The third case is m and n are both even. So that we have 8 sine to the fourth y cosine squared of y dy. What we're going to do this time is make two substitutions. We are going to substitute sine squared x equals 1 minus cosine 2x over 2, as well as cosine squared x equals 1 plus cosine 2x over 2. Why are we going to do this? This is to reduce the powers by half. Because we've taken a squared and we're going to have a first power here. So what we're going to do on this one is we'll take out the 8. We'll take this is sine squared of y squared cosine squared y dy. So sine squared is 1 minus cosine 2y over 2 quantity squared times 1 plus cosine 2y over 2 dy. Now this is not an easy problem at this point in saying what do we do with this. The common idea would be to take it and multiply everything out. But what's going to happen when we do that is we're going to get a fairly complicated integral. And there's a better way. First we can reduce out the 8 and the 2's. Okay. Having a thought about some of this stuff can help. So what do we notice here? We have a plus and a minus. If we multiply these two together, we're going to get 1 minus cosine squared of 2y dy. Now why is that good? Because now we have a problem that's similar to what we've done before. We can make a substitution for this 1 minus cosine squared, because that will be sine squared of 2y. Then we have 1 minus cosine 2y. Now what? If we multiply this out, we'll get sine squared 2y minus cosine 2y times sine squared of 2y. And all of that's multiplied to dy. This is nice because I know the derivative of sine squared is cosine. Or I shouldn't say, sorry, the derivative of sine is cosine. So I can do a straightforward substitution with that. And then how am I going to deal with this sine squared? Well, that's basically the situation we're starting with here. We have m and n are even. M is 2 and n is 0. So we can say, let's separate these two things out. On this first one, we can say let u equal sine 2y du will be 2 cosine 2y dy. Then, when we do this, we can just ignore this for a little bit. And we have cosine 2y dy there. We have cosine 2y dy. This 2 is going to have to move to the other side. So we'll have 1/2 du. So we'll have u squared times 1/2 du. So we'll take that 1/2 out in front. So we'll have negative 1/2. And then the antiderivative of u squared would be u cubed over 3. And we'll tack on a plus c there. On this one, we're going to have to do that substitution just like we started with, 1 minus cosine 2x over 2, except this time our angle is 2y. So that would be, and again, we have to be careful about this kind of problem that we'll realize we're just doing a substitution here. We're not integrating yet. This will be 1 minus cosine of 4y because it's 2 times whatever that angle is, and the angle is 2y there. So 1 minus cosine of 4y all divided by 2 dy. We can take that 1/2 out in front. The antiderivative of y, or of 1, is y, minus the antiderivative of negative cosine 4y, well, we'll just leave the negative there, is going to be sine 4y over 4, because when we take that derivative of sine 4y, the 4 comes out. It's reduced there. And at this point, we just need to plug back in what the u value is, and we can get rid of the parentheses there. So we have 1/2 y minus sine of 4y divided by 8 minus sine cubed of 2y divided by 6 plus c. And that's the last of our cases for using trig products for sine and cosine.